Hello, everyone, and thank you for joining us today. Welcome to Megger's monthly testing tactics webinar series. Today's topic is Transformer Turns Ratio Test Beyond the Basic Facts. My name is Michael Fleischer, and I'm the Digital Marketing Specialist from Megger. I'll be acting as the moderator for today's presentation and supporting you on any technical issues or questions for our presenter. On the right side of your screen, you will see a control panel that looks similar to this one. You can submit questions at any time during the presentation by typing in the box highlighted in red, and I will read the questions out during the Q&A segment at the end of the webinar. All webinar attendees are eligible to receive one NITA CTD and one PDH or zero point 0.1 CEU for attending. You will receive this in an email within 2 business days of the webinar. That email will also include a copy of the PowerPoint presentation and a link to the video recording of the webinar if you'd like to watch it again or share it with your colleagues. Remember, you can ask questions at any time during the presentation and they will be answered at the end of the webinar during the Q&A session. Our presenter today is Daniel Carreño, Megger Applications Engineer. Also to assist with the question and answer session, we will have 2 panelists joining us today. Ken Petrov, Megger Product Manager, and Volny Naranjo, Megger Senior Applications Engineer. Okay, let's go ahead and get started. Thank you for joining us today, Daniel.
Thank you, Mike. Good morning, and good morning to everyone joining today's session. Right, this webinar is gonna discuss TTR testing. Right, for all of you in the audience that are familiar with transformer testing, you know that most often than not, when we hear about TTR testing, we think it's pretty simple, and in reality, performing the measurements is pretty straightforward, right? Pretty quick. We get an assessment on the condition of the transformer's winding and core uh, status. So again, a pretty simple test, and because of that, sometimes we overlook some of the factors, both related with the transformer itself and also with the unit that we use to make the measurements. So today we are going to focus on those factors that again sometimes we overlook and obviously can impact the results of the measurements we are taking, right? So we're going to start with a very brief introduction, some of the basic concepts of TTR testing, right? So to make sure everyone we all are in the same page in regards to these measurements. Then we're gonna go right into those factors again. First, what are those parts of the transformer that, or technical aspects of the transformer that can affect these measurements, as well as the instrument and the technique that we are using to take those measurements. So going right into it, starting with the basic concepts of the test, right? And first, we need to understand why this measurement is important, right? And as you see in the slide, I wanted to first show the importance of a transformer in the power grid system, right? Starting from generation, as you can see, I will start seeing transformers right away to be able to transmit that energy, and then when we reach industrial customers and then lower voltages, right, like consumers in a city, for example, we need transformers all along the system, right? So we will see obviously different kinds of transformers, but again, throughout the whole power grid. So obviously making sure that these elements of our system are in good condition is of paramount importance. And obviously one of the basic functions of a transformer is to deliver power from one circuit to the other, most often than not, also either stepping up or stepping down the voltage, right? So it's one of the very basic functions of a transformers, and being so, we want to make sure that the transformer is complying with that relationship between the voltages of those two circuits in the simplest case, right? So that's what the TTR test is going to do for us when we measure it on any given transformer. So again, just as an example, obviously the pictures you're looking at right now are not to scale one to another, right? If we start from the left, from your left, start seeing a small pole mounted transformer, then we're going to distribution type transformer, path mounted, for example, then going into power transformers, and all the way to the right, an example of what is called a GSU, a generator step up transformers, right? Again, pictures not to scale one to each other. So obviously the transformer in the right, pretty large in size, obviously high, excuse me, higher capacity, higher voltages. But in terms of the DTR test, we actually performed these measurements the exact same way on all of these transformers I'm showing you. So how do we run the test itself, right? Now in this slide I'm showing you a simple two-winding three-phase transformer. So we connect the device that will apply voltage on one side of the transformer and measure the induced voltage on the other side of the transformer. In this case, this example I'm showing you, on the high voltage side of the transformer, and measure the induced voltage on the lower voltage side of the transformer. Right? We calculate the relationship, and that's gonna be our ratio. So that's in very simple terms the way we perform the test. Once again, we apply voltage, in this case on the high voltage side of the transformer, measure the resulting induced voltage on the other side, in this case the low voltage side of our transformer. So what are we measuring, right? I mean, the name of the test is transformer turns ratio, right? And as you can see here, what's highlighted in this transformer equivalent circuit is that relationship, right? The amount of turns that I have on my primary winding compared to the amount of turns that I have on my secondary winding, right? But again, per definition, we're trying to measure the relationship between those two numbers, which are the number of physical turns I have on each of my windings. In reality, as users, owners, or the individuals assigned to run the test, we don't really know how many physical turns the windings of our transformer has, right? Is not a number, is not a factor that's identified in the nameplate. Is not gonna be in any of the maintenance manual or any of the dimensions drawings that we get from the manufacturer, right? So again, as the individuals running the test or even the owner of the transformer, we most probably will not know the number of actual physical turns in the transformer. So what do we do about that, right? So I'm showing you here once again that equivalent transformer circuit diagram, right? And again, per definition, transformer turns ratio is the relationship between physical number of turns, right? What I have right now highlighted in red. Then we get to another concept, which is transformer nameplate ratio, right? Like I said, we don't have an actual indication in the transformer nameplate or any document related to the transformer that will tell us that those numbers. What we do have in the nameplate is the rated voltages for both my primary and secondary windings, right? We're obviously discussing the simplest two winding transformer case. So with that, I can also do a relationship and get what is called transformer nameplate ratio, right? If I take the primary voltage divided by the secondary voltage rating, then again I get my transformer nameplate ratio, my TNR, which is highlighted in yellow. If we go back to our explanation of how we are running the test, right? We said that we apply voltage on one side, measure the resulting induced voltage on the other side. Then we're actually performing what is technically called transformer voltage ratio, right? We take those two values, the voltage we apply, the voltage we induce, and we get that relationship. So we get our TVR. So now we need to think again, what is the condition in which we run the test, right? When we run the test, we obviously we don't have, or we have the transformer isolated, we don't have any load connected to it. In other words, we're testing, or we're performing TTR on an open circuit condition, right? Our secondary side again is open. We have no load connected to it. We're only measuring that induced voltage, and that particular condition allows us to say that or those quantities we are measuring, the voltage we are applying, the voltage we are inducing, that relationship is equal to the actual transformer turns ratio because we are testing under no load or open circuit condition, right? So that is the condition that will allow us to say that TTR, the TVR we're actually measuring, is equal to the TTR, and that's what I have sort of in the center in the slide. Okay. Now we've been discussing again the simplest two winding transformer case, right? But we can also have, and it's probably most common, that we're testing a three-phase transformer, right? Still a two winding, but now in this case a three-phase transformer, right? On those transformers we can have several different vector configurations, or in other words, the way our windings are internally connected to each other, right? So I'm showing you here in the slide just a few examples. Obviously not these are by no means the total number of possible vector configurations there are for a three-phase transformer. Again, just a few examples, right? We go from one phase to a delta delta, a YN0, and a DYN1. Again, just a few examples. Depending on which vector configuration my transformer is, I will need a TVR recalculation factor, right? I need a correction factor depending on the vector configuration in my transformer, so I can at the end compare what I'm measuring to the calculated TVR, right? Once again, if depending on the vector configuration of my transformer, I would need that correction factor. Showing you two examples in the slide, right? First, a DYN1 transformer. So what I have to do is find that transformer configuration in my table, right? And then I would know that my recalculation factor is square root of 3. So I will take those two rated voltages from my nameplate, do the relationship, right? The high voltage divided by the low voltage, and then use the recalculation factor to obtain my final TVR, my calculated TVR, which then I will use to compare to my measurements. So again, in the first case, D1N1, my table is telling me my recalculation factor is square root of 3. What happens if it's the opposite, right? I have a star or a Y-connected winding on the high voltage side and then a delta on the low voltage side of my transformer. Well, same thing. I look for that particular vector configuration in my table, find the right correction factor, and use it to calculate my final TVR. So let's do a quick, easy example. I know this is pretty simple, but again, want to make sure that we are all in the same page in regards to this calculation. So I have a nameplate here for a simple D1N1 transformer, right? 600 volts on the primary, 480 volts on the secondary. So my initial nameplate ratio, right, 600 divided by 480 equals to 1.25. I go to my table. I know that for a D1N1 I need to multiply that 1.25 by square root of 3. So I do that, I obtain 2.165 as my calculated TVR, right? So at the end, I will use this final number 2.165 to compare to the actual measure value that I'm getting from my TTR instrument, right? Again, is the final number the one that I get after multiplying my TNR by that recalculation factor, depending on my vector configuration of my transformer. Okay. So now that we are familiar with those very basic terms, what is the basic terminology that we use for TTR testing, let's get into understanding a little bit of the results and how we can correlate those numbers to other tests, other measurements that I can perform on my transformer to at the end give a full assessment of the condition of both the windings and the core of my unit. Okay, so when we run the test, obviously, like we've been mentioning already, we get right our measure voltage ratio, right? The actual, what it's in this table called actual TTR. And I said that we compare that number versus or against the TNR multiplied by the recalculation factor, right? Doing that comparison, we can calculate the percentage, what we call the percentage error, right? How far my measurement is from the actual calculated value that I get from my nameplate. By the IEEE standard, that percentage error should not be more than plus minus 0.5%, right? Obviously, if I get a percentage error larger than that, it means that I have an issue or my transformer has an issue related to the windings or the core of my transformer. But those two numbers are not the only ones that we get when we perform the test. We also get excitation current and the phase deviation, right? Very important to note that, again, for those that are already familiar with transformer testing, you know that excitation current is a measurement that is voltage dependent, okay? So obviously we run, or typically, if you're running an excitation current test per se, the industry standard to do that is to run it at 10 kV if the rating of the transformer allows us to apply 10 kV. Then again, the industry standard is to run it at 10 kV. Obviously, we don't do a TTR at that voltage. So again, the number the actual excitation current will be different because we are using a different voltage. But we can actually compare the pattern, right? One of the ways to analyze excitation current is to look at the pattern that we get on each one of the phases of my transformer. So that should match, right? The pattern should match if we run the test at 10 kV or if we are using the voltages or lower voltages for our TTR. So in terms of the pattern that we get, then we can use that as a tool to also um, analyze the condition of my transformer. And then the phase deviation, I should get a number that is close to 0 or 360 degrees, right? This is phase deviation and not the phase angle between my two windings. So again, this is directly related with the quality of my core. So if I get a number that is far from that zero region, then it means I have an issue, most probably related with the core of my transformer. So what is the relationship between these numbers, right, the TTR of my transformer, to other measurements that I can do? Or in other words, what can I do if I run my TTR and I get unexpected results, right? A percentage error that is greater than plus or minus 0.5%, or my phase deviation is too large, or the excitation current pattern that I was expecting is not appearing in my results. So what are the other tools from that toolbox, right, that I have to assess the condition of my transformer? What else can I do to confirm or to investigate further a possible problem with my transformer? So as you can see already in the slide, I'm highlighting from all the toolbox that I have. Winding resistance will be one, excitation current as we already mentioned, right? But we can do a formal excitation current test and a sweep frequency response measurement. So how are those related to TTR? That is easier to explain using this matrix that I got from the technical brochure 445 from C. Gray, a very nice tool again to see that relationship between the different tests and obviously the parts of my transformer. You see in the matrix that when we talk about winding ratio, we are primarily looking at the winding condition, right? The turn-to-turn insulation and also the integrity of the core, right? If, for example, we have a severe issue with the turn-to-turn insulation in any of the windings of my transformer, if that is bad enough that is affecting ratio, would most probably also show up in winding resistance, right? If I have previous results of winding resistance for that transformer, I will see again if the problem is bad enough. It will also show us a different winding resistance value for that particular winding. Magnetization current, and also looking at the winding turn-to-turn insulation and the magnetic circuit integrity, right? In other words, the core, the condition of the core of my transformer. And finally, the frequency response analysis, right? What is normally called SFRA. More specifically, if we look at the inductive interwinding test, we can get a very good approximation of the ratio using the flat magnitude response that is in the lower frequencies less than 60 Hertz. We calculate the reciprocal of the magnitude in that part of the curve. Again, we can get a very good approximation of the TTR value. In other words, if we have a problem with TTR and we can also run an SFRA, we can use the tool to confirm an issue in that regard with our transformer. So now that we understand a little bit more of the results, again, what will happen if, or what do we do if we get unexpected results, right? What can we do to make sure that if we do get an unexpected or higher than expected percentage error in the results, or our, again, the pattern in the excitation current is not what we were expecting, the phase deviation is larger than expected. Is this because I have an actual problem with my transformer, or is this because, again, factors related to the actual transformer we're testing, with the unit that we are using for the test, or the technique that we are using to run the measurement can be improved, or in other words, can I do something else about it before I deem my transformer with an issue? So to understand a little bit better on that regard, we need to look again at that equivalent circuit of the transformer and think a little bit with more detail on what is actually happening when we run the test, right? Like we explained at the beginning, we used an instrument that will use a source to apply a voltage on one side of the transformer, measure the resulting induced voltage on the secondary. But again, how does that happen? So we apply the voltage, again, most commonly on the high voltage side of my transformer. That voltage will in turn establish a magnetic flux, right, that will couple with the help of the core in our transformer with our secondary winding, and then in turn induced a voltage on that secondary winding, right? So that flux that we establish and then the response that we get from that secondary winding is called mutual flux, right? And it depends obviously on the winding construction, the core construction, how the phase, or how those two windings are assembled in the internal part of my transformer. So there are several factors that will affect how that relationship, or how that phenomena is achieved. Uh, One of them is the excitation voltage, the voltage that we use to run the test, right? Second will be the technique in terms of where or which side of the transformer we apply the voltage on, either on the primary winding, or the high voltage winding I should say, or the low voltage winding. If we apply voltage on the high side of my transformer, then we do what it's called a step down measurement, right? We are stepping down the measuring the voltage. The voltage that we're inducing will be lower than the one that we are applying. And if we do the opposite, if we apply on the low voltage side of the transformer, then we're stepping up, right? The technique is called step up measurement. Another or third factor that will directly impact the result of my measurement is if I either do a paraphase measurement. This obviously concerns to three-phase transformers. So very often we have instruments that will have connections for the three phases, but internally we only will have one source. So those instruments will apply voltage on each phase at a time, and then at the end present the three phases result. But again, the way the unit is actually running the measurement is in a per phase phases. Okay, so let's look at some. But first, I want to show you these two diagrams comparing the step down technique versus the step up technique when running this test. Right, on the left, you look at the step down ratio test. Again, we apply voltage on the high voltage side of our transformer, measure on the low voltage side, right? And if you see, if you look at the equation, you will see that with this technique, the error that we're gonna get is gonna be always on the positive side, right? The voltage that we're using is always lower than the one that we are applying. Compared to the step-up technique, again, the voltage that we apply is always lower than the one we induced on the higher voltage side of our transformer. And again, this will impact the results greatly. I'll show you some examples of how that plays or how that will result in terms of the ratio error that we get. Also, looking at the mutual inductances, right, in each one of the cases, M12 on the step down technique, M21 on the step up technique. Think about it, M12 is always going to be lower than M21, and the reason of that is most transformer construction wise, the low voltage winding, it's wanted closer to the core, right? And obviously the high voltage will be outside of the low voltage side winding, and that results in better coupling between the two windings. And again, that also will greatly help us to achieve more accurate readings when we do either step up or when we use higher voltages for the test. So let's look at some actual examples of these factors, right? These different choices that we can make when running the test. So on this example that I'm showing you right now, a DYN1 transformer, 138 kV on the high side, 4.365 on the low side, and running several different measurements starting at 8 volts, as the excitation voltage, right? We're running the test first at 8 volts. We obtain 0.73% ratio error, right, outside the IEEE limits, right? So what happens when we increase that excitation voltage without changing anything else? Just go from 8 to 40 volts, then things start to look a little bit better. 0.27% of ratio error, right? We are already inside the limits. Go to 80 volts, 0.16%, 125 volts, 0.10%. And again, on this case, we're running the test with a Paraphase technique, right? So the unit that we had connections for 3 phases, but is running measurements 1 phase at a time, right? Very important to note that by increasing the voltage of the test, we're not making our transformer better, right? It means that for this particular transformer, because of its construction, because of its size, it means that we have some voltage dependency, right? And 8 volts is not enough, or in other words, we get bad coupling between the two windings, and again, 8 volts is not enough to achieve an accurate reading of the actual TTR of that transformer. Let's look at another example. This one is interesting. It can be confusing at first. So in this case, YN0 transformer, 13.2 kV on the high side, 480 volts on the low side. On this one, we were doing a three-phase energization from the low voltage side, right? So a step up technique. And if you look at all three phases, right, you see a trend, a pattern that as we increase the test voltage, again, at first the graph can mislead a little bit the audience, because we say, okay, for two of the phases, phase A and phase E, right, the errors were on the negative side, and as we increase the voltage, that error tend towards the positive, or in other words, towards zero, because again, the error that we were getting at lower voltages is negative. And the same happened with the middle phase, which is B phase, and the error also tend to go towards the positive side, because on this case the error was already positive. Looks like it got worse, right? I mean, it actually increased. So we went from a value close to 0.15 to something closer to 0.2. So yes, it got worse, but on the other two phases it got closer to zero. And another important thing to note on this graph is that starting from 200 volts going to 250, the value didn't change as much as it did from 48 to 200, right? So in other words, like we said in the previous example, transformer is showing some voltage dependency, right? After 200, our value is not changing much, so we reach the threshold of that excitation voltage at which that number is not going to change. We're actually getting an accurate reading of the TTR for that transformer, and at the end all of our three numbers, right, at 250, are well within the 0 point or plus minus 0.5% error allowed by the IEEE standard. So one more example, right, comparing 8 volts, 24 volts, and 48 volts excitation voltages. On this case, doing the traditional step down measurement, applying voltage on the high side of the transformer. Then you see all three phases, the error tended to go towards zero, in this case negative, as we said earlier. Why? Because we are increasing the voltage. So one more example now. In this case, applying on the low voltage side of my transformer, right, also increasing voltage, starting with 3 volts, 6 volts, then 12 volts. In this case, the error is going towards the positive side, right? In this case, phase A was on the negative side of the error, so it's going towards zero. The other two phases going away from zero, again, because we are increasing voltage, is going towards the positive, because we are applying voltage on the low voltage side of my. Okay, so that was excitation voltage, right? How our results are going to change depending on the construction of my transformer and how the excitation voltage that I'm using to perform the measurement will affect my reading, as well as what technique I am using, either step up or step down, right? Which is the one that we want to compare right now. The previous examples, even though we are also showing a few different cases applying on the high side or the low side, we were comparing mainly the change when we switch or when we use different excitation voltages, right? So now let's compare these two techniques. step down versus step up, right? In this case, a YND transformer, single phase excitation, right? Doing one phase at a time. And on green, step down, right? The traditional technique applying on the high side, measuring on the low side. We're getting around 0.35 for phase A, close to 0.4 on phase B, close to 0.5 on phase C. And we switch to single phase excitation step up, right? Applying on the low voltage side. And you see, even using a considerably lower voltage, only 8 volts, so 1/10 of what we were using with step down, were much better results. Percentage errors in case of phase C, very close to zero, right? So better accuracy. On this other example, if we look at all the ratio measurements of a transformer with a tap changer, right? 17 taps. In case of step down, the traditional technique, we see that more than half of our taps were outside the limits, right? More than 0.5% error. And then when we switch to step up, in this case I don't have the data in terms of the voltage, but again, just comparing step down versus step up. On the blue curve step up technique, all of our taps are well within the percentage error, and not only that, you'll see that the transition between one tab to the other is also more uniform, right? So I think you can see that in the curve when you compare the blue curve to the orange one, way more uniform, and again, more importantly, all of our tabs are well within the 0.5% allowed error. Another example with a tap changer, in this case a load tap changer, 33 taps. Probably worse case than the previous example with the numbers all over, right, ranging from around minus 0.3 all the way to 0.7%, right? So very scattered results for all three phases. Step up excitation, a lot more uniform. You see, even this, I mean, the scale is different, but all well within the 0.5% plus or minus, and again, more uniform results for step up excitation. Finally, what happens when we compare per phase versus three-phase excitation? We first compare changing the voltage that we are using to excite that winding where we're applying the voltage, right? Second, we compare step up versus step down. And now we want to compare single phase versus three-phase excitation. Will the result change if I do phase by phase measurement compared to energizing all three phases at once? As you can see in this example, and hopefully you can see that, I mean, at first glance, looks like this graph is only showing two cars, but if you look closely, there are 6 cars, right? The one in the bottom, I mean, also paying attention to the y-axis, most of our results are in the negative side of our graph, right? So most of them are negative. So when we compare per phase excitation, right, pretty uniform transition between taps, but you'll see that when we went to three-phase excitation, energizing the three phases at a time, our results, all of them shifted towards zero, or became, in this case, smaller, right? So again, more accurate reading when doing a three-phase excitation versus doing a per phase excitation. And Not like the previous example on this one. I mean, the tab number 5 was barely on the limit of the minus 0.5% limit. Again, you can see when switching to three-phase excitation, all of our results gotten closer to zero, so more accurate. One more example, right? On this case, when we did single-phase excitation, all of our readings were in the negative side, and we also did different voltages, so 3 volts, 6, 12, and 15. You see that when switching to three-phase using the same voltages, we had consistently lower percentage errors. Right? So the value that we were measuring was closer to that one that we calculated from the nameplate ratings of those two windings. And the final source of error is transformer configuration, right? Depending on what type of vector configuration I have on my transformer, might need to take certain routes to get a more accurate readings. For example, if you look at the lower right corner of the slide, initially when we discussed the concepts, right, for TTR testing, we said that for us to say that the actual measurement we're taking, the voltage ratio is equal to the TTR of the transformer, we need one condition, and that condition is that that winding that we are inducing the voltage to should be open circuit, right, or have no load on it. If we are doing a single phase excitation, that is described in this lower right diagram, then the other two phases that we are not testing, on this case on the secondary having a delta, are loading the winding under test in that particular moment, right? So that initial condition is no longer valid, and that will affect the accuracy of the readings in that case. What happens when, for example, I have a Y connected winding, but I don't have a neutral accessible, right? So I need to take the precautions to to actually have the right calculations to get the right number to compare to the values that we can measure with our instrument. And nowadays, modern instruments, modern TTR instruments will have provisions to help the user a lot, right? We'll have the tables we discussed. It will calculate the ratio for you when you enter the nameplate values. So it's really important that we configure the unit that we are using correctly. And now that we know certain things like three-phase energization is better because it will help me get more accurate results when I have a delta on that secondary side where I'm measuring the induced voltage. Or what if I have a phase shifting transformer, an auto transformer? Again, modern units will help me a lot in that regard, both with the calculations and doing the proper technique depending on the transformer that I'm testing at any particular situation. So in summary, right? TTR will help me assess the condition of both the windings and the core of my transformer, right? If I do find or I get unexpected results, I can go to that toolbox from different tests that I can perform to further investigate, use winding resistance to confirm insulation issues on my windings, excitation current to check both the windings and the core, or the sweep frequency response as an alternative to get a very good approximation of the actual TTR of my transformer. And that there are factors that will affect my readings directly, either related to the transformer construction, right, mainly the configuration, or factors coming from the test set that I'm using, the voltage that I'm using to excite the windings, either if I'm using a step up versus step down, or doing a per phase versus three-phase excitation, right? Some of the best practices to get more accurate TTR readings are avoid the delta loading, right? If you have a delta on the secondary side, avoid the loading of the winding under test. And how do you do that? Well, using a three-phase excitation. Be aware of the voltage dependency, right? We showed some examples where as we increase the test voltage, we'll get more accurate results closer to the calculated value for that particular transformer. We can also maximize mutual flux between the two windings, right, under test. And we achieve that with both higher voltage, the step-up technique, right, applying voltage on the low voltage side of the transformer, or doing three-phase excitation. Paying attention to the ratio error of the, with the direction of each change. When you change the technique is a good tool to determine where to go next, right? I should say, I haven't mentioned it before, but when you decide to do up, a step up measurement, you need to be aware or make sure that you are using the proper instrument to do so, right? We are trying to induce a higher voltage than that one that we are applying. So again, we need to make sure that we are not inducing a dangerously high voltage on the high voltage side of the transformer under test, and also that the unit that we are using can handle that voltage, most importantly in a safe manner, in a safe condition. And now that we discussed again some of the basics of the TTR, how do we interpret the results, what are the factors that will affect my readings, let me take the final couple minutes just to walk you through. Not giving you a very detailed description of our product line, but just so you are aware of the Megger offering in terms of TTR testing. We have I'm just showing you kind of the most representative unit on each one of the families per se, starting from the handheld units, very small, used to test single and three-phase transformers up to 1 MVA, right? So mainly distribution transformers, battery powered, so pretty small. Again, it's a handheld unit. Then we go into the hand crank TTR. We have had this instrument for many years. It's pretty reliable, very high accuracy, plus minus 0.1%, in a portable design. I should say that just like my initial pictures of the transformers, the pictures here are not to scale to one another, right? So obviously the handheld is not half of the hand crank TTR. Is actually way smaller than it looks in this slide. So then we go to the TTR 300 series, right? So that unit will allow me to connect to three phases of my three-phase transformer simultaneously. It will do the measurement phase by phase. It will allow me to test higher ratio transformers up to 41,000 to 1. Then we're going to the MWA, which is also a three-phase unit, in a way that will allow me to connect to the three phases of my transformers, but will measure the TTR on a phase-by-phase basis. It will offer me also winding resistance measurements. That's the nice thing about this unit, is a combination, so I can do TTR and winding resistance without changing leads on my transformer. And finally, the true three-phase DTR, right? The transformer ratiometer, a true three-phase. So this unit will actually energize the three phases of my transformer at a time, up to 250 50 volts of induced voltage. It will allow me to do both step up and step down technique. It has a mode that will actually automatically choose the best method for the particular transformer under test. Very high accuracy guaranteed, plus minus 0.5% in a very wide range of temperature, which is really important. I mean, those features combined allow this unit to provide a very easy method to test both phase shifting and zigzag transformer. So that's a huge advantage as well if you need to test those types of transformers. It's small for what it does. It's really light when you see the unit. I mean, you really don't believe how light it is. And when you do a three-phase test, it will test in less than 10 seconds. So pretty quick as well. And with that, I'll take it back to Mike before we take any questions. He has some announcements to do, and then we'll come back to take questions from the audience.
Thank you, Daniel. At this time, the presentation portion of the webinar is officially concluded. We will now take 30 minutes to answer as many of your questions as possible. If you have any questions, please submit them into the Q&A box on the right side of your screen. For those of you that are leaving, when you close the webinar window, a survey should pop up on the screen. We would greatly appreciate it if you would take a couple of minutes to provide your feedback so we can continue to improve upon future webinars. On the survey, there's a field where you can also request a demo or quote on any Megger products. A copy of the presentation, along with the link to the video recording of the webinar, will be emailed to everyone in about a week. You can also view video recordings of previous webinars on our website at us.megger.com/webinars and register for next month's webinar, Fundamentals of Power Factor Testing and Advantages of NBDFR. The presenter will be Dinesh Chazer, Megger Technical Support Group Manager. Now let's get to your questions. Our first question is for Ken. Should the vendor specify how the ratio test was performed, or is it easier to assume that it's a step down TTR?
Yep, sorry about that, just had to unmute my mic. So the question is about how the results come from the vendor. Should they specify in step up or step down? For us, it doesn't matter because turns ratio is turns ratio. It doesn't matter which way it was performed. We'll be able to match it using the true three-phase TTR to the specified nameplate and using the IEEE standards.
All right, thank you. So Daniel, I have the next question for you. When is it better to use step down measurements or step up measurements?
In general, we can say that you have or you will get more accurate results when you do step up, right? And as we discussed it during the presentation, there are certain transformers, certain configurations where that step up technique is even more advantageous. One example is when you have a transformer with voltage dependency, or when you have a delta on the primary side, right? But again, in general, we can say step up will give you more accurate readings.
And I just wanted to hop in here and say that the true three-phase TTR has an auto mode for testing, and that will determine the best way to test the transformer by default. So you don't have to choose if you want to do step up or step down. The instrument removes that decision making that's required and provides you with the most accurate result.
All right, thanks. Real quick, I am going to let everyone know we are going to be sending out a copy of this video that we try to show, as well as the PowerPoint presentation, along with your professional education certificate with the information we were provided when you registered and logged into the presentation. That will be going out early next week. For the next question I have is also for Ken. As per IEEE, can you tell the amount of primary voltage we can apply to perform TTR? Is this dependent on what PRI and SEC voltage we are testing for that specific transformer? For HVTR testing, do we need to perform that test at a very low voltage, or can we do the testing close to HV level of the transformer?
So in the IEEE standards, it specifies that you need to test at or below line voltage and at or above line frequency. And those are the measurement criteria. So, on a 765 kV transformer, if you can generate 765 kV and measure it and then get the ratio on the low side, more power to you. But in general, we test up to 250 volts, and we've shown that when you induce that amount of voltage on the primary, it gets you results that are accurate to plus or minus 0.05% of the nameplate.
All right, thanks. The next question for Volney. Would there be any issues if two transformers of different vector configurations, say DYN5 and DYN1, are paralleled on low voltage side?
Okay, so this question is not directly related to the turns ratio, but it's very important because that's one of the things that you verify when you're testing TTR, that you have the correct vector diagram. And so definitely different vector configuration transformers can be connected in parallel, but you have to be careful how you do that. You need to match the vector or the phase deviation on the phase. So you need to check that your degrees or your phase deviation matches, so you don't create a short circuit. So you need to analyze how the phase deviation is going to be on each transformer, and then you connect according to that on the low voltage side.
Thank you. Our next question, Ken, what about when we test an ARC furnace transformer with an open delta secondary?
So for those particular transformers, with the true three-phase TTR, you are able to energize all three phases simultaneously, but you can also energize a single phase at a time. So when you deal with an open delta, the only way to test those is to test those one phase at a time, which is the test mode that you can select during your test setup.
All right, Daniel, our next question, how do you place the jumpers on a DY connection with no accessible neutral?
Okay, so in this context, the TTR testing, we don't need jumpers. Understanding jumpers is just short-circuiting two of the bushings of a transformer. So we don't need any jumpers to run this test. If this question is about the connections, right? He's saying he doesn't have or the transformer doesn't have an accessible neutral on the secondary. No problem, just connect to the three bushings, right? X1, X2, X3 that you have. But it's important that is that the user tells or configures the proper vector configuration in the instrument that is using for the test. That way, the instrument will select the proper correction factor for the calculated TTR, and then it can compare it to the measured value.
All right, Volney, next question is, the legs are symmetrical, but the results are not. Why is that?
Okay, so I guess this question is related to three-phase transformers in which you see two excitation currents identical or very similar for phase A and phase C, and usually B phase is a little bit lower. So this happens because the circuit, the magnetic circuit that phase B sees is different than the magnetic circuit from A and C. So it's a magnetic circuit with less reluctance, so there's going to be less resistance or less current in the circuit. That's the reason B phase is always a little bit lower.
Thank you. Ken, do we have a product that can work down to -40 or -50 C?
The true three-phase will work in conditions down to -20 C. The leads can be brought out, say, of a truck cab that is heated to at least that temperature, and then the leads can be connected to the transformer and operated. So technically, yes, we can work down to that temperature, but the unit must remain at -20 degrees or warmer.
Thank you. Next, for Daniel. Do you recommend that all the transformers be tested in the step-up configuration, regardless of its application, in order to obtain the lowest possible percent error?
But like we mentioned before, in general, yes, that will yield better or more accurate results. But like also Ken mentioned, if you have a unit like the TTRU3, the unit in its auto mode will select the best method for a particular transformer. Now, if you don't have a unit like the TTRU3, and if you want to perform step-up measurements, you need, like I mentioned at the very end of the presentation, you need to be mindful of the possible high voltage that you are inducing on the high side of the transformer. Again, if you have a unit like the TTRU3, the unit will perform the test safely, will select the proper voltage to run the test. And if you don't, you need to be mindful of that voltage that you will be inducing on the high side of the transformer.
All right, Ken, we have one question for you, or for any of the panelists that would like to jump in. For the YD transformer and the correction factor of √3, are the percent errors still high? Can they be improved?
So with a YD transformer, this goes back to one of the slides that Daniel was talking about. If you have a D on the secondary and you are performing single phase step down measurements where you're exciting one phase of the Y and measuring the other phase, the corresponding phase of the D on the secondary, then the other legs of the D that are unenergized will influence the measurement that you will get. So the best way to overcome the loading of those unenergized phases is to excite all three phases of the Y simultaneously. With the true three-phase TTR, you can do that. But again, we would do the measurement in step up where we would excite the three phases of the delta and then measure the induced voltage on the Y primary. So yes, the percent error will be improved so long as you excite three phases simultaneously.
Thank you. It looks like that's all we have for questions today. We apologize for any issues we had with GoToWebinar today. We will be in contact with them to try and sort out any issues in the future. A copy of this recording, of course, will be sent out on Monday to all participants, along with a copy of the PowerPoint presentation. If you have any questions, please reach out to us at support@megger.com. Everyone, please have a wonderful weekend. After the presentation, you will be prompted with a survey to take to let us know how we did. We understand we had technical difficulties today. Please keep in mind how we did with our presenter for those of you who had correct audio and visual. That being said, everyone have a terrific weekend, and we hope to see you at the next one.